everyone, and welcome to Introduction to Aerospace Engineering. My name is Aliya and I will be your teaching assistant for this course. This is the first time I'm teaching this course, so if something is unclear during the lecture or you have a question, feel free to call my name and ask it. Okay, let's see our agenda for today. Today I will talk about what aerospace engineering is, what it consists of, and for the rest of the class we will focus on aerodynamics, which is one of the main disciplines of aerospace engineering. So what is aerospace engineering? It is a branch of engineering that deals with design, development, building and testing of aircraft and spacecraft. Here I highlighted just a few of the projects that are going on today in aerospace engineering, and I will talk about them a little bit more so that you could have an idea of what aerospace engineering is. Let's start with Airbus A380. This is the largest passenger aircraft ever built. It can carry about more than 500 people at a time. And you can see the seating configuration here. So it fits 10 people in a row, and also it is a double deck. So you can imagine how many people can fly in one flight. It weighs around 600 tons, so you would wonder how this heavy machine can go up in the air. The answer is aerospace engineering. Next is SpaceX Dragon capsule. This is remarkable because it is the first private spacecraft to dock the International Space Station. It delivered the necessary supplies to astronauts, but SpaceX is working on the next model of Dragon that will be able to deliver people to International Space Station. And you've probably heard about this one in the news. It is Curiosity Mars Rover from NASA. And it is a Mars science laboratory that will investigate the surface of Mars and find out if it's possible to support microbial life there. So you would question how this car-sized object was delivered millions of miles away, and there was a 7-minute communication delay. But it was still possible, and it's there on Mars, and the answer is aerospace engineering. Also, you've probably heard about this guy, Felix Baumgartner, who jumped from 24 miles above the Earth's surface. He was the first person to achieve supersonic speed, that is, the speed higher than the speed of sound. And he was not in a vehicle at that moment. So he broke a world record and achieved a speed of 840 miles per hour. What made it possible for him is his pressurized suit from David Clark Company, which pioneers in designing protective equipment for pilots and astronauts. So one of the world records was broken because of aerospace engineering. Next is Boeing Phantom Eye. It is a reconnaissance drone, and drone means that it does not have a pilot inside. It can fly autonomously or it is controlled from ground station. And Phantom Eye is remarkable because it runs on liquid hydrogen instead of conventional fuel. So it can stay up in, liquid hydrogen is more efficient than ordinary fuel, so this aircraft can stay up in the air for 4 days without refueling, which makes it a pretty good deal for the defense industry that can make surveillance for more time now. Next one is Lockheed Martin SR-72 aircraft. It is in development currently, but Lockheed Martin claims that when it's ready, this aircraft will be able to achieve speed that is 6 times higher than the speed of sound. And in order to do that, the engines should be modified, should be redesigned completely, because conventional turbojets are not capable of achieving those speeds. And here you can see NASA's Flying Saucer spacecraft. It really looks like a flying saucer. and it is actually ready for its first flight, but weather conditions were not optimal, so the first flight test was delayed. But this spacecraft is designed to test heavy payload landing on Mars. And why do we need heavy payload? Because NASA hopes to put humans on Mars, and human habitation model weighs a lot. And the final project that I want to highlight today is SpaceX Falcon Heavy rocket. It is also in development currently, but when it's ready, it will be the most powerful rocket that was ever built after Saturn V, that was used to deliver people on Moon. But SpaceX's goal is even more challenging, to put people on Mars. So Falcon Heavy will be one step on achieving that goal. So I've covered just a small part of aerospace engineering, but you can see that it pushes the boundaries of impossible further and further every day. And if you decide to pursue aerospace engineering, hopefully one day you'll take part of a project like this. Aerospace engineering is divided into several disciplines. You cannot call yourself just an aerospace engineer. You need to have expertise in one of the fields below, but also you need to know other fields so that you can communicate with other people in your team. So some of the main disciplines of aerospace engineering are aerodynamics, which studies the motion of objects in the air; propulsion, which is how you choose the engine and the fuel that you want to use to push your vehicles forward; structural analysis is how you build something that is capable of achieving the goals of the mission and that can meet the requirements on the loads that will be put on aircraft or spacecraft. Materials science is which materials you choose so that your mission can be accomplished. And stability and control. This is how you control your aircraft or spacecraft and make it go where it needs to go. And today we will focus on aerodynamics. We will talk about what is it and where it's used. And also we will learn basic principles of aerodynamics, such as what makes the airplanes fly and what forces affect the flight, what are some of the basic performance and flow parameters, and also how in real life things are more difficult than described in theory. So let's start. Aerodynamics studies motion of air around moving objects. Aerodynamics is applied not only in aerospace industry but also in automobile industry and even sports. Aerodynamics is mainly used for design of better performing aircraft and spacecraft and in other industries as well. But today we will focus on aircraft. So for example, using aerodynamics, these engineers can test a model of aircraft in the wind tunnel, and later they can modify this model so that it will become the optimal one. Another example is how you make better design decisions for spacecraft. So why the re-entry vehicle is blunt-shaped and not sharp-pointed. You would logically conclude that sharp-pointed objects have less drag, but aerodynamics can explain this. So you will learn, if you pursue aerospace engineering, you will learn a lot more about this later, but for now just believe me. So when objects travel with speeds of greater than speed of sound, their shock waves occur. So in the first example, you see that the object is sharp-pointed and the shock wave is attached to it. That makes this shock wave weaker than the other shock wave that occurred here with the blunt shaped body. So in the first case, the temperature behind the shock wave, that is here, will be lower than the temperature behind this shock wave. That means the object in the first case will heat up more than the object in the second case. And this makes it better because we can come up with materials that will withstand the temperatures on the descent of this capsule with astronauts, for example. Alright, so now let's learn the basic principles of aerodynamics, and we will proceed with the whiteboard. Let me get it here. Okay, so before we start, let us review some variables that we know from physics already, but these variables are used a lot in aerodynamics. I got my marker. Okay, so let me write it down. Fundamental variables. The first one is pressure. And pressure is normal force acting on the surface of a unit area. So let me define it here as force divided by area. And so if we have a surface like this, which is of unit area, the pressure will be the force that acts on this area. And the force should act perpendicularly in order to measure pressure correctly. So pressure is measured in newtons per meter squared, or in English units, it will be pound force per feet squared. So I hope you remember this from your physics. This is just a quick review. The next variable is density. And density is how much substance you have in a unit volume. So density equals to mass divided by volume. If you have a volume, a unit volume, like this cube for example, then the density of the substance inside this cube will be equal to mass of the substance divided by the volume. Alright, and density is measured in kilograms per meter cubed, Or in English units, it will be slugs per feet cubed. Alright, and the final variable that we will use a lot today is velocity. And I will write it down like a small v here, so that we will not confuse it with volume. So velocity is the rate of change of position in time. So if we have position denoted by x, or like here, velocity will be derivative of x with respect to time. And velocity has a magnitude, which means that you can have high speed or low speed. Let me denote it here as small vector, small arrow and big arrow. But also velocity has a direction, which means you can go in this direction or in the other direction. And that makes velocity a vector quantity. So that means if either of them changes, velocity changes. And if your speed stays the same but direction changes, that will change the velocity. Okay, so we've reviewed that, but now, since we will study aircraft, we need to learn some of the terminology of the aircraft. And it will be just wing terminology because we will cover just basics today. So let's look at the wing from the top. We will see a shape like this. So first of all, we define this distance from one end of the wing to the other end. It is denoted as B and is called a wingspan. Let's write it down. B is the wingspan. Alright, next one is the area of the wing. So wings can be different shapes, but area is measured without taking into account the shape. So let's denote it as S. Also, it can be called planform area. Next, we have some air coming at the wing. It travels at some speed that we denote as V infinity, which means free stream velocity. That is the velocity far from the wing. Let's write it down as well. Free stream velocity. Next is this edge of the wing. It is called the leading edge because it's the first one to meet the flow of air. Leading edge. And obviously there's also the other edge of the wing, which is called the trailing edge. And it's the last one to go into the flow of air. Okay, and the last variable that we will use today is the distance between the leading edge and the trailing edge. It is called chord and is denoted by C. So C is chord. Alright, so this is the top view of the wing, but let's look at the wing from the side. So if we cut out a section of the wing, we will have a shape like this, and you will learn today why wings are shaped like this. So if we look from the side, we still have the chord, but also there's one more important variable, that is angle of attack, which is how much the airfoil, so this shape is called the airfoil or profile of the wing. So angle of attack is denoted by alpha, and it is how much the airfoil is inclined with respect to the free stream flow. Let me write it down here. Alright, so this will be good enough for today's lecture for wing terminology. Now let's actually learn why the wing flies. Let me erase this part now. So in order to understand why wings fly, let's start with airfoil in the wind tunnel. Let's draw it here. So this is our airfoil and the wind tunnel. So wind tunnel basically just imitates the flow of air as if the airfoil was actually flying in the air. So if we follow one particle into the wind tunnel, let's see what we have. One air particle comes here and goes around the airfoil and exits at the other side. And if we follow another particle, it will do exactly the same. So what can we conclude from here? We can say that whatever mass enters the wind tunnel also exits at the other side, because the walls of the wind tunnel cannot make any particles leave the wind tunnel. So this is called principle of continuity. That means mass flow in equals mass flow out. Let's write it down. Okay, let's introduce some numbers here so that we can mathematically write it down. So let's name the inlet as 1 and the outlet is 2. The area of the inlet will be A1 and the area of the outlet will be A2. So principle of continuity will tell us that m.1 m1 dot is equal to m2 dot. That dot means the derivative with respect to time. So mass flow, how much mass is entering the wind tunnel per second, is equal to the same mass exiting the wind tunnel. Okay, now let's remember what mass is. Mass is equal. Let me write it down here. Mass equals density multiplied by volume, right? And what is volume? Volume is area multiplied by distance for which that area is transferred. So area is A, rho is distance, and let's say x is the distance. So now we have this equation. Let's substitute this expression into this equation. That will give us, so we said that dot means the derivative with respect to time. Let's write it down as m dot equals derivative of mass flow, how much mass enters the wind tunnel, by time in 1 second. So if we substitute now this expression here, we can say derivative of rho a x per time, so dt. And now it's time to make some assumptions. So let's say that the air that enters the wind tunnel is the same air that exits. That means the density of this air will stay the same if we assume not the supersonic flow. So that means the density is constant, and in this case it will be incompressible flow. So we can take density out of this expression of the derivative, and then area obviously stays the same by geometry. So that will give us derivative of distance with respect to time. And we remember that this expression is equal to velocity. So that means we can write it down here. And that means that mass flow rate is equal to density multiplied by area multiplied by velocity. So now we can substitute this expression for m dot in this equation. Let's do it, and we will get rho 1 A1 V1 equal to rho 2 A2 and V2. So what can we conclude from this expression? If density stays the same, we can cross it out from both sides of the equation. The areas are the same by geometry, so we can cross them out, and that will give us that V1 is equal to V2. That is, the speed at which the air enters the wind tunnel will be the same as the speed at which the air exits the wind tunnel. So it's pretty logical. But now let's see what happens if we change our wind tunnel a little bit and put the exit right here above the airflow. And we'll make our wind tunnel like this. Let's call this area A3. So the same mass should still go through here, through this part, which is A3. But principle of continuity still applies. So we can say that M1 dot, whatever enters in the wind tunnel, should be equal whatever is passing through this point here, which is equal to M3 dot. And then if we substitute the same expression for mass flow rate, this will give us rho 1 A1 V1 equal to rho 3 A3 V3. And we can make the same assumption for the density. We assume the incompressible flow at low velocities. And this will leave us with A1 V1 equals to A3 V3. But we know that A3 is a lot smaller than A1. Let's write it down here. So A3 is smaller than A1. And this will, from this equation, we can conclude that V3 should be greater than V1 for the equation to hold. So this will give us our first conclusion, that the velocity of the air in the section with smaller area is larger than the velocity of the air with the section with larger area. Okay, so let's memorize this. We will use it later, as you will see. And now let's derive the Bernoulli's equation. Bernoulli's equation. So, in order to derive Bernoulli's equation, we apply basic physics principle that energy can be neither created nor destroyed. So that means that total energy is always conserved, but what makes total energy? It is a sum of kinetic energy and potential energy. So let's write it down. Total energy is equal to kinetic energy plus potential energy. But this is for large objects and it's mainly used in physics. But in our case, we're concerned with volumes more than any other study. So let's find out what the energy is per unit volume. So we can divide this equation by volume. So total energy per volume is equal to kinetic energy per volume and plus potential energy per volume. Now let's remember what kinetic energy is. Kinetic energy is 1/2 mass multiplied by velocity squared. Let's substitute this expression into this equation. So total energy per volume is equal to, let me put potential energy first here, and is equal to, we substitute the expression for kinetic energy, which is 1/2 mass multiplied by velocity squared and divided by volume. And we can see here, we know this quantity, mass of substance per unit volume, it is equal to density. So we can substitute density into this equation. Plus 1/2 rho v squared. Alright, so we know one part of the equation here. But what is potential energy per unit volume? Let's think about it for a bit. Can I erase here? Okay, so let's imagine we have a unit volume of some gas in a cube. And this gas has some pressure inside. Now, potential energy is the ability to do work. So what kind of work can the gas in the box do? Let's think about it. So if we open up the box, open one side of the box. So here it's still the same, but this side can move. So if we let this side of the box move, what will happen? The gas inside will move this side of the box for some distance because of the pressure that was inside. And it will move this side until the pressure of the gas will equal the pressure outside the box, until the equilibrium. But that means pressure can do work on the side of the box when moving it for some distance. So that means that pressure is a potential energy per volume of a gas. But since the gas is inside and it's static, we call it static pressure. So let's rewrite this equation with our conclusion from here. So total energy per volume will be just total pressure, and potential energy per volume will be static pressure. And we add the quantity, that is 1/2 rho v squared. Okay, now, so if this is total pressure and this is static pressure, this quantity should be some kind of pressure as well for the equation to equal. So since it has velocity, we will call it dynamic pressure because it's moving, and we denote it as Q. Q equals 1/2 rho v squared, and this is dynamic pressure. Alright, now let's write down this equation with substituting dynamic pressure. So total pressure will equal to static pressure plus dynamic pressure. And this equation is called Bernoulli's equation. And using this equation, we will learn why the wing is able to fly. So Bernoulli's equation. Alright. Now let's apply this equation to our wind tunnel. Let me erase it here. Okay. So for inlet 1, if we apply Bernoulli's equation, we will get total pressure should be equal everywhere inside the wind tunnel. But for inlet 1, we will get P static 1, static pressure at inlet 1, plus dynamic pressure at inlet 1. But let's substitute the expression for dynamic pressure. It will give us 1/2 of rho 1 v1 squared. And this should be equal to total pressure is still equal inside the wind tunnel. And this will, if we consider area 3, we will have that P static 3 plus 1/2 rho 3 v3 squared. Now let's rearrange this equation a little bit. So this will give us P static 1 minus P static 3 equal to 1/2, and we assume that this is incompressible flow, which means the density is constant. So we can assume density is equal to rho everywhere, and we have velocity 3 squared minus v1 squared. But remember that v3 was greater than v1 from what we found out before. So that means if we subtract v1 from v3, it should be greater than 0. But that will mean that this side of the equation should be greater than 0 as well. And that will give us that P static 1 is greater than P static 3. Now let's think about this for a little bit. So P static 1 is pressure here, but also if we had a wind tunnel straight, whatever pressure the air enters here will be the same while it's moving through the wind tunnel. So P static 1 and P static 3. So if P static 1 is greater than P static 3, what will happen to our airfoil? It will tend to move to the area that is less pressure. So it will tend to move where? It will move upwards. It will have a force that acts to the area with lower pressure. In this case, it will be upwards, since velocity of air above the airfoil is greater than the velocity of air below the airfoil. And what is this force? So this is our famous lift force. It is denoted as L. And this is why airfoil and wing and aircraft is able to fly. So let's write down that lift is an aerodynamic force that results from pressure distribution on the surface of airfoil. So aerodynamic force due to pressure distribution. Alright, now it's time to define other forces that act on the aircraft. There's also drag that results from pressure distribution, but it's a lot smaller. For good, well-designed airfoil, drag should be a lot smaller than lift. So let's draw the plane here. We found out that it has lift upwards, and then drag is a force that occurs for the same reasons as lift, but it should be less, and it opposes the motion of the aircraft. Motion forward. But what enables the aircraft fly is thrust that occurs from the engines. Thrust is denoted as T. So this is thrust, and this is drag. And there's obviously weight that acts on everything on our planet, and it's denoted by V. So you can see that there are four main forces that act on the aircraft during flight. Alright, now let's proceed on to how lift is calculated. Okay, we can get rid of this metal. Hope you have it in your notes already. Alright, so lift is equal to dynamic pressure multiplied by the platform area multiplied by CL. This formula was determined theoretically but also proven experimentally many times. And let's define drag at the same time. These are two main aerodynamic forces. Drag is equal to dynamic pressure multiplied by platform area. It's almost the same, but the coefficient is CD. So what are these coefficients? CL is called lift coefficient. And CD is called drag coefficient. Now, so imagine if we had two airplanes, one very small that fits into wind tunnel, and the other one is Airbus A380. If we calculate lift, they will be drastically different from each other. So we cannot make any conclusions by just looking at the value of lift. But CL is a coefficient, so that means it is dimensionless. And these two coefficients enable us to understand how good the airfoil performs. So these are called performance parameters. And it was determined that CL and lift coefficient and drag coefficient depend on angle of attack and also on two other dimensionless numbers, which are Mach and Reynolds number. So let me define them. Let's write it down that CL and CD are functions of angle of attack, alpha, Mach number, and Reynolds number. And CD is the same. It depends on the same coefficients. But let's see what Mach number is. Mach number is the ratio of the speed of the flow to the speed of the sound. let's define it here as velocity to A. So this is Mach number, and A is speed of sound. And what is Reynolds number? Reynolds number is a measure of viscosity of the flow. Reynolds number is defined as density multiplied by velocity multiplied by chord over the airfoil and divided by viscosity. So this is called Reynolds number. And mu is viscosity. So high Reynolds number mean that viscosity is low. So we can assume that the flow is inviscid. This is true for low velocity flows. And low Reynolds numbers mean that it is high viscosity flow. So it's called compressible flow. And you will learn about that more if you pursue aerospace engineering. You will learn more about it in your courses. And depending on Mach number, flows can be supersonic, subsonic, or transonic. So if Mach is less than 1, this will be a subsonic flow, which means flows with speeds lower than the speed of sound. And supersonic is the speed greater than the speed of sound. So lift coefficient and drag coefficient, they depend on these numbers. And let's see how lift coefficient depends on angle of attack. It was determined that lift coefficient varies with the angle of attack according to this, like this. The graph, the dependence looks somehow like this. So we see that as we increase the angle of attack, the lift coefficient increases. So that means the airfoil will produce more lift. But at some point it will stop producing more lift. It is called a critical angle of attack, AC. And after that, stalling occurs. That means there is less and less lift as you increase the angle of attack. So I think this is good for today, but when we talk about airfoils, we consider the wing from the side. So that means we considered a two-dimensional flow. We assumed that the wing was infinite when we have an airfoil like this. But in reality, the wings are three-dimensional. So that means the physics are a little bit different. And if we consider finite wing and 3D flow, we will see that an effect like this occurs. It is called vortices, and when large aircraft flies, you can see after that a spiraling flow of the air. This occurs because pressure below the wing is larger than pressure above the wing, as we learned today. So when they meet at the end, the flow below the wing wants to go up since it has less pressure here. And this makes this effect of spiraling. And this is called vortices. And that is why aircraft use winglets. This decreases vortex effect drastically. And when the vortexes are small, this decreases drag as well. And that is why winglets are used in commercial airliners to make them more efficient. So this concludes my presentation for today. And if you have any next time we will cover propulsion. And if you have any questions, this is time to ask. Thank you for your attention. See you next class.